inside our body, we have all these different types of processes which are catalyzed by enzymes. So in order to actually study the behavior of enzymes and how they catalyze reactions, we have to study the rates of these enzymes and the rates at which they catalyze the reactions. Now, one way in enzyme kinetics that we study the rates of reactions is by plotting the following curve. Now, on the curve, the y-axis is the reaction velocity V0 of that particular enzyme. And that's basically the rate at which the enzyme catalyzes its particular substrate. And the x-axis is the concentration of the substrate S that binds onto the active site of the enzyme. So what we essentially do is we carry out an experiment. So in the experiment, we have a beaker. In that beaker, we have the enzyme that we want to study. Now, initially, in the beaker, we don't have any concentration of substrate, and so the concentration is 0. And because no substrate is present in that beaker, no substrate will be bound onto the active site of the enzyme. And so the velocity, the rate of that enzyme will be 0. And so in trial 1, point number 1 is 0. Now, in trial 2, we then add a certain amount of concentration of S. Let's say this many S molecules, and then we measure that corresponding Y value, that velocity of that enzyme. And so let's suppose we get the following value, and so this is data point number 2. And now we add even more S concentration. And let's say we add this quantity that corresponds to this data point here. And so we continue adding these data points, and eventually every single time we do this for any enzyme, this is the curve that we're going to obtain. So notice what the blue curve tells us. Initially, at the beginning, when we have a relatively little amount of S in that mixture, this blue curve will resemble a straight line. So from about here to about here, this blue curve looks like a straight line. And what that basically means initially, when we add a small amount of concentration of S into our mixture, the rate, the velocity of that enzyme, the rate at which the enzyme catalyzes the reaction will be directly proportional. So we'll have a straight line with respect to that S, the concentration of substrate. But as we continue increasing the concentration of S, we see that the slope begins to decrease and the curve begins to level off. And eventually it approaches asymptotically the maximum velocity of that enzyme given by the red curve. Asymptotically means the blue curve never actually crosses that red line. So that horizontal red line basically describes the maximum rate of activity of that enzyme at which the enzyme can actually operate on that substrate and transform it into some type of product. This is what the blue curve actually describes. So to see this in equation form, let's take a look at the following equation. This equation basically describes what is taking place inside that beaker once we add the substrate. So initially, we have the enzyme by itself, and then we add the substrate, and the substrate is also by itself. But then what begins to happen is the substrate begins to bind onto that enzyme's active site, and we form an intermediate molecule known as the enzyme-substrate complex. Now, going this way, the rate constant is K1. But once we form some of this complex, it begins to dissociate back into these two reactants, and the rate constant of that reverse reaction is K-1. At the same time, some of that complex, so we now have the substrate inside the active site, and the enzyme will begin to transform that substrate into the product. And once we form the product, it will dissociate from the active side to basically form these final molecules, the product and the enzyme in its individual form. Now going this way, the rate constant is K2, and going in reverse, the rate constant is K-2. So this is the equation that basically describes what is taking place inside the beaker once we reach equilibrium, once we establish equilibrium. Now, what we essentially want to do in this lecture is we want to derive the mathematical equation, the mathematical expression that basically describes this blue curve. So can we derive such an equation? And the answer is yes. But before we actually begin our derivation, we want to simplify this equation. So instead of using the equation that describes equilibrium, we're going to assume that we're essentially at the beginning of that equation. So right at the start, when the time is approximately equal to 0. And at this point in time, the velocity of that enzyme is equal to V naught. Now, another important point about the beginning of the reaction is, right at the beginning of the reaction, we have not yet formed a large amount of product. So right at the beginning, what happens is we have that enzyme that binds onto the substrate, and this takes place relatively quickly. And so equilibrium is established here between these and this complex quickly because this takes place very quickly. But the enzyme basically converts that substrate to the product relatively slowly. And so at least initially at the beginning, we don't actually form a lot of the product. So at a time of t approximately equal to 0, what that means is because we don't have a lot of product formed, this reaction will take place at a very, very low rate. And so by approximating that, we can essentially remove this entire equation and remove the k minus 2 term. And that's because this reaction takes place at a negligible rate. So once again, to simplify this equation here, we can instead study the reaction at the beginning, that is when the time is approximately equal to 0, right at the beginning of that reaction. And that point in time, the rate V is equal to V naught. So at this moment in time, very little product P has actually formed. And so the reverse reaction of the formation of the product, this reaction here becomes negligible, and we can basically remove that from our equation, and this will simplify our equation, and that will allow us to actually derive the equation that we're looking for. So this is the equation that we want to use. Now, what exactly is our starting point? Well, the starting point is right here. So we essentially begin by studying how that enzyme is functioning. And to study how the enzyme functions, we have to actually look at the enzyme as it is bound to that substrate. So in this particular case, so this is our starting point. And that's exactly where we get equation number 1. So equation number 1 basically gives us the rate law of this reaction here, as the enzyme actually has the substrate at the active side and it transforms it into the product. And so the rate law of this reaction is given by equation number 1. So the rate of this, which is the V naught, remember, the y-axis here describes the rate at which the enzyme actually transforms the substrate that is bound to the active side. And so this V naught is the same V naught that we have along the y-axis here. So V naught, the rate at which the substrate is transformed in the active side, is equal to the product of the rate constant K2 of this reaction multiplied by the concentration of this molecule, the complex, this intermediate molecule. By the way, these are reactants, these are products, and this is an intermediate molecule that exists between the reactants and the product. Now, the problem with this equation is, remember, we ultimately want to basically derive a mathematical equation that describes this curve. And so what that means is, whatever this equation is, we have to be able to describe V naught in terms of the concentration S of the substrate. And this equation has ES. And what that means is we can actually use this equation and we have to somehow replace the ES concentration with the S. And that's exactly what we're going to do in all these steps, as we'll see in just a moment. So in the next step, we basically want to ask ourselves, once we form this enzyme substrate complex, well, first of all, how do we form this enzyme substrate complex in the first place? Well, to form this, we have to go in this direction. And what's the rate law for the formation of this enzyme substrate complex? Well, that is given by equation 2. So the rate of formation of this enzyme substrate complex is equal to the product of the rate constant K1 and the concentrations of these two reactants. So E and S. Now, once we form the ES can basically go in two different ways. It can either go on and form this product, which is basically this equation number 1 that we described here, or it can go back and reform these two reactants. And equation 3 gives us the dissociation of that substrate from that enzyme. So the rate of dissociation of the enzyme substrate complex is equal to the product of the reverse reaction K minus 1 multiplied by this quantity here. Now, our ES complex doesn't only dissociate going this way, there's also a probability that it will dissociate going this way. And so when it dissociates going this way, we have K2 multiplied by the concentration of ES. So this basically describes the entire rate of dissociation of the enzyme substrate complex. So it can dissociate not only going this way, but also going this way. And that's why we have these two summations. So we sum this with this, and that gives us the rate at which our enzyme substrate complex actually breaks down. So before we actually continue, now we have to make an important assumption. And the assumption that we make is that our reaction is at a steady state condition. And what a steady state condition actually means, the intermediate that is involved in our reaction, the concentration of the intermediate is not changing. And the only intermediate we have in our reaction is the enzyme substrate intermediate. So what that means is the concentration of the enzyme substrate complex is not changing. And what that implies is the only way that this concentration is not changing is if this reaction going this way, if the formation of the enzyme substrate complex is equal to the dissociation of that enzyme substrate complex. So assuming the steady state condition, the concentration of the enzyme substrate complex will remain constant. And this means that the rate of formation of the enzyme substrate complex is the same as the rate of dissociation. So equation number 2 is equal to equation number 3 because we make this assumption of a steady state condition. So once again, a steady state condition means this concentration remains unchanged. And the only way that's true is if this K1 reaction is equal to these two reactions here. So the breaking is equal to the forming. And so that's exactly what we do in this step. We essentially equate this equation to this equation here. So we have K1 multiplied by these two concentrations is equal to K minus 1 multiplied by ES plus K2 multiplied by ES. Notice on the right side we have these two same terms, and we can bring that out of our equation to get the following result. And now we can basically bring all the concentrations to the left side and all the K values, the rate constants, to the right side, and we get this equation. So the product of the concentration of the enzyme and the substrate divided by the complex concentration is equal to K minus 1 plus K2 divided by K1. And instead of using these three rate constants, we basically set this ratio equal to a new ratio defined by uppercase K with the M subscript. And this is known as the Michaelis constant. And the Michaelis constant is actually a very important constant, as we'll see in the next lecture. And the units of Michaelis constant are concentration. So we'll talk much more about this in the next lecture. And let's designate this as equation number 4. Now, if we take this new equation, this is equal to this, and rearrange it and solve it for the concentration of the enzyme substrate complex, we get equation 5. So we essentially bring this to this side, and we bring this to our denominator here, and we get equation 5. So the concentration ES is equal to E multiplied by S divided by Km. Now, for a moment, let's go back to that assumption that we made at the beginning. We said that we're looking at the reaction in its initial stages when the time is approximately equal to 0. Now, initially, when the time is approximately equal to 0, we have a lot of the substrate that hasn't actually bound onto the active site of the enzyme. And this means equation 6. So the total substrate found inside our beaker is equal to the substrate that is not bound to the active site of the enzyme plus the substrate that is bound onto the